Jack, I am you in 2025. I hoped it wouldn't come to this. The repercussions of sending a message to myself in the past could be catastrophic, but I've no choice. The world is coming to an end due to the over-reliance on fossil fuels. I need your help to save it. You must design the ultimate wind turbine given the following constraints. Clockwise rotations about a horizontal axis with no more than 3 blades. A maximum angular velocity of 3000 rpm. A maximum mass of 500 grams. A maximum diameter of 500 millimeters. It must self-start at 10 meters per second, and the maximum power should occur between a tip-speed ratio of 3 and 8. I'm running out of time. You will need help. Find Group 10 in Roderick Hill 252 at Imperial College. The fate of the world is in your hands.
Group 10, I need your help. Tell me about your design.
The design was divided into 2 major sections, aerodynamics and structural analysis. The primary objective of the aerodynamic design is to optimize the power output of the wind turbine while keeping the weight to a minimum. The first consideration is the number of blades. Ideally, a maximum of 3 blades should be used for higher power output. However, more blades increases weight and induces more skin friction drag. 1 blade would reduce it, but the need for a counterweight for the turbine to remain stable makes it inefficient. The next best option is a 2-bladed turbine. Using the maximum diameter of 500 mm, more power can be extracted as a result of the maximum area being swept. According to this graph by Professor Graham, the maximum efficiency of small wind turbines is at tip-speed ratio between 3 to 4 without inducing high viscous losses. TSR of 3.5 is chosen because this allows the design to have a small area while staying in the most efficient range.
The Reynolds number under the given conditions was found to be approximately 70,000. As this is fairly low, our decisions were based on the paper New Airfoils for Small Horizontal Axis Wind Turbines from the University of Illinois. The best airfoil for this mission was the SG6043 because it has the highest lift-to-drag ratio of all the potential choices. It is used for the majority but not all of the blade. The SG6042 is used at the blade tip for manufacturing purposes due to the SG6043 being too thin. The root has an elliptical shape as it has little effect aerodynamically but experiences large centrifugal load. This root then blends into the thicker SG6040 airfoil, which optimizes for very low Reynolds number near the root. Our wind turbine also uses a monocoque design on the nose cone and the blades, so it allows a smaller hub. This significantly decreases the mass of the turbine, as aluminium is much denser than ABS plastic. The hub is made to have the shape of an octagon as it's closer to a circle, making it more surface efficient while being securely fixed within the cone.
The blade is most efficient if the circulation is approximately constant along the span. To achieve the optimized angle of attack of 8.05 degrees throughout the span of the blade is designed to twist according to the change in relative velocity. By using Schmidt's optimized design equations, both the twist and chord length distribution were calculated. Here is a graphical representation of the twist angle and chord length distributions. Here is a virtual model of the design made in cryoparametric. This is done by using the twist and chord length distribution to discretize the blade into 21 planforms and blend them together. Since the rapid prototyping machine can only print objects up to 200 mm, our design must be separated into 3 sections. The cut at the blade is made to be a dovetail shape so that the parts can lock up on each other. It is also rounded so that there wouldn't be stress concentration on angle junctions.
The structural integrity of the blade design must be able to withstand the forces acting on it. Note that a maximum airspeed of 12 meters per second is used for safety calculations. There are 2 types of force acting on the blade, which correspond to 2 potential failure modes. Centrifugal forces cause parallel failure, and aerodynamic forces, including lift and drag, cause perpendicular failure. Assuming constant density throughout the blade, the centrifugal force at a planform on the blade is the sum of centrifugal forces acting on all the elements between that planform to the blade tip. The stress is obtained by dividing this force by the respective planform cross-section area. Here is the distribution of centrifugal stresses. The blade root experiences maximum centrifugal stress of 0.7 megapascals.
For aerodynamic forces, the lift and drag distribution is produced by using the values of the chord length. They are then resolved into force distribution Q in the y and z axis. The bending moment is then calculated by integrating this force distribution along the blade. Assuming that the deflection is much smaller than the length of blade, the stress distribution by aerodynamic forces can be calculated using the bending moment found in beam theory as shown. The total stress is calculated by propagating centrifugal stresses with aerodynamic stresses. Here's the stress distribution. The maximum stress is 5.7 megapascals, which is lower than the ABS plastic fail tensile stress of 21.6 megapascals. The deflection can be found using beam theory as shown by these integrals. The tip deflection is calculated by propagating the deflection in the x direction caused by forces in the y and z direction. This corresponds to 2 mm deflection and 0.9% elongation, which is smaller than the ABS plastic brick elongation of 3.18%. Thus, our design will not fail at 12 meters per second wind speed. The wind turbine is now ready for manufacture.
This is how the world is saved. Here is our performance data and maximum CP and TSR. After testing, we realised there are a number of problems wrong with our design. Firstly, it is too heavy. The hub size could have been dramatically decreased, and the nose cone and central section of the wind turbine could have been much smaller as well. Our safety factor was 4 times higher than the maximum stress in the blade and was definitely overkill. With a lower mass, we could have significantly increased our merit function. The TSR chosen was too low for a 2-bladed wind turbine, and our maximum CP was only 0.13. The maximum TSR was 3, while our design was for 3.5, so at a higher wind speed this could have been achievable. Although the aerodynamic performance was reasonable and the turbine self-started immediately at 6 meters per second, we should have designed a wind turbine with a higher tip-speed ratio to increase the power output. Overall, we designed a robust turbine which generated power but could have been much lighter.